that were done in the 19. Okay, there's a little, hold on, just a little message I got here. There we go. The first computers that were done in the 1940s and early 1950s, the ones that were based on vacuum tubes, they were actually based on physics principles that were discovered in the 19th century. And these would be things like Ohm's law, electrons, Gauss's law, those types of things. And if you know physics, there was a revolution in the 1920s, about 100 years ago, in quantum mechanics. New principles were discovered with regard to quantum mechanics, and it was was sort of brought to a head at a conference that was held called the Solvay Conference, that people like Einstein and Born and Heisenberg and other people came up with new theories of physics that we had not known before. And the interesting thing is that the computers we use today really don't use most of those, or have not up until now used those theories. So semiconductor technology came along, in the 1950s, 1960s, and people started making some semiconductor-based computers. Those started to use a few of those concepts, but a few of the key concepts that were discovered 100 years ago have really not been leveraged up until very recently. Let me talk a little bit about those. Okay. So these concepts are, not intuitive. One of which, the first one, is called superposition. We're all familiar with digital electronics with bits that are either 0 or 1, but you can actually have a particle or some state that might be somewhere in between, not in between, but both simultaneously. And that's called superposition. And you can leverage that, I'll talk a little bit later about, to make a more powerful computer. The second one is very strange. It's called entanglement. Albert Einstein called it spooky action at a distance. You can create two particles like two photons, and they can be separated by millions of miles, but they're sort of entangled so that if one changes state, the other will change its state at exactly the same time. So this does not allow you to do communication faster than light, but it is a phenomena that we see, and that's, people take advantage of that for both quantum computing as well as creating quantum networks. Just like we have an internet today, people are now doing research on the quantum internet that will exchange these entangled particles to communicate information. And then the third, which some of you may be familiar with, is called interference. And some of you may have actually performed, maybe in college, a double slit experiment where you could have two waves. And the important thing there is that you can have two waves, and you can have constructive interference, which will make the patterns lighter, as shown there, or you can have destructive interference, which will have the two waves cancel each other out. And the quantum scientists have figured out a way to use that in order to make calculations. So the key thing is, you want to build a computer that can process information and run algorithms much faster than you can with the supercomputers we have today. That's the whole point of quantum computing. And by providing the researcher with these new tools, essentially, superposition, entanglement, and interference, people are able to construct algorithms that can calculate things, and some things, not everything, but some things faster than you could possibly do with a classical computer. So This is my only slide that has math on it, but it does show some of the key principles of the what are called qubits. I think we're all familiar with digital bits, either 0 or 1. These entities, these things that will carry the information in the quantum computer is called a qubit. So as I was saying earlier, qubit can be, it's like a superposition of 0 or 1. The representation for that is this little sphere there. It's called a Bloch sphere, where you could still have 0 and 1. 0 would be the North Pole, 1 would be the South Pole, but you can essentially measure the state so it's on the equator of that sphere, and that is something where it's a probability of 50% 0, 50% 1. But the other interesting thing about a qubit is, even though you can put a qubit in that thing, at some point you measure it, and when you measure it, it collapses. It'll either go to a 0 or either go to a 1, and on a probabilistic basis. And the thing that is, again, not intuitive, it is not deterministic. You could do it a 1,000 times, and let's say it is on the equator, so it's a 50% probability of 0 or 1. It's like flipping a coin 1,000 times. You don't know what's going to come up, but roughly at the end of your experimentation, you'll get this 50%, 50%. And it doesn't have to be, of course, 50-50. It could be 75%, 25%, or 90%, or 1%. But when you write a quantum program, essentially what you're doing is you're manipulating that qubit so that it goes into these various states to calculate what you want. The other thing that a qubit has, which is again very non-intuitive, is it's called the no cloning theorem. If you're a digital electronics engineer, one of the most common things is you have a signal and you'll amplify that signal, and maybe you make 2 or 3 copies of it to go to other portions of the chip. You cannot do that with a qubit. And that's one of the key properties that will allow you to do quantum communication in a way that you can't be intercepted by a hacker. If I were to send one of those qubits to Donn, and there was someone in the middle, a hacker who's in the middle, in a classical computer, what that person could do is if it was just a classical bit, 0 or 1, he could intercept that thing, read it out, copy it, and then send it on to Donn. But if you send a qubit and it's in one of these superposition states, when they read it out, it goes to 0 or 1, and he can't copy it. He can't reproduce it anymore to send it on to Donn. So that's one of the reasons why people talk about the quantum internet, so that you can construct a network which is can't be intercepted, can't be hacked, and this is getting important. You'll see it more and more. I'll take questions at the end if you don't mind. Now, we talk about qubits. There's something like 9 or so different ways of building a qubit, and this is where the industry is exciting. And we're still in a very early stage, and there are many different proposals, many different ways of building these qubits. There's over 100 companies or organizations that are building various forms of quantum computer. I'll start with the one on the right, because I know that's Donn's favorite, is photonics. Yes, you can use photonics. You can build interferometers. There are single photon detectors, those types of things. One of the ways you can encode the states is by the polarization. In this diagram here, vertical polarization would be a 1, horizontal polarization would be a 0, but then you could have an angle. But again, you could create, and there are devices called single photon generators that will generate it. You can put it at a, let's say an angle tilting to the left, and one by one you send those photons. You pass it through a polarization filter, let's say a or vertical polarization filter, or maybe a Silberman mirror. And again, 50% of the time, the photons will come out one polarization, 50% of the time they'll come out with the other polarization. So there's several companies working on photonic-based quantum computers, but there's also other means. Another mean is superconducting, where you take a circuit where you cool it down to like 15 millikelvin. That's just slightly above absolute zero. That's like 1,000 times colder than outer space. And people like IBM and Google are building quantum computers that way. You can take an ion and you can trap it, and you can measure that. You can take a single electron, and electrons have a property called spin, where you can have spin up and spin down to represent the 0 or 1. And again, if it's a superposition stage, it's like it's in both at the same time, as well as other technologies. So photonics, since this is the group we'll talk about, photonics, you can have these things that don't use any photonics at all, like a superconducting does not actually use any lasers or anything like that. You can have something where everything is photonic, like the one on the right, a photonic qubit, with interferometers and those types of things. But some of these technologies in the middle, like the trapped ions and some of the others, one of the more interesting ones, I don't have it on this chart, I should add it, is called neutral atoms. They're manipulated by lasers. So you can take, there's a concept called a optical tweezer, where you can take an atom and have lasers shine down, and the lasers can move it along the chip to be a certain pattern. That's used in neutral atoms. You can then shine the laser on that atom to create what's called a quantum gate that will change its state. Let's say change it from a 0 to a 1, 1 to a 0, or put it into one of these superposition states. And then you can use a laser to read it out. So optics are important for some of these technologies. Optics, again, or photonics is very important, of course, for communication, because all quantum communication is going to be done over a fiber optic cable, which is, of course, photonic, and I'm sure many of you are familiar with that. Just to show you the diversity worldwide, we count on our website, we count the number of different projects that are building these things, and we see 125 organizations, over 159 different types of projects, and you can see that count there of who's doing what. The most popular one is something called superconducting. The leaders there are people like IBM and Google, a startup company in Berkeley called Rigetti. But there are others that are working on trapped ions. A startup company called IonQ, Continuum, which is actually a spinoff of Honeywell. It has been working on trapped ions. Intel is working on what's called spin qubits. Intel's trying to leverage their semiconductor manufacturing capabilities, very advanced semiconductor manufacturing. So the spin qubits are very similar to a transistor type of technology, and very, very active worldwide. I'll show you in a couple slides the amount of investment that's being made. So people want to understand, why does this work? And the way to think about this, you have to perhaps have some computer science background, but this graph here is the way that computer scientists think about algorithms. And what they think about is, how does the time to execute scale with the size of the problem? And I'll give you a very simple example of that. Let's say you have a list of items, it's an unordered list, and you say, find a specific value in that unordered list. You have to go through that list one by one until you find the match. And, probably, again, worst case, you have to go through the entire list because the very last one's going to match. If you double the size of that list, your runtime is going to double. But perhaps another example is, let's say you want to take that unordered list and you want to sort it. So it's in, perfect thing. There are algorithms, they teach this in college, one of the most simplest algorithms is called a bubble sort. And if that list is n times long, it's n squared number of operations you have to do to sort that list. So computer scientists measure this runtime, and they classify the various algorithms to do these things according to that. And so the first example, of course, is linear. You double the list, you double the thing. The second one is called polynomial. So it's n squared. But there are some problems that it expands really, really rapidly. One of the problems that people, again, taught in most colleges is called the traveling salesman problem, where, and the idea of this, I don't have a diagram, but the idea of this is you have a salesman who has to travel to n number of cities, and and there's distances between each of these cities, you want to figure out the path that's the shortest to go through all those routes. Turns out that at least one of the algorithms is n factorial. And if you have to go to something like 100 different cities, n factorial or 100 factorial is zillions, very, very large, and it's beyond the capability of a classical computer. So that's what we show here. This blue line here in this presentation shows how some of these classical algorithms can get very, very inefficient as you increase the number of elements in the problem. And the key to quantum is that people can come up with a different algorithm that takes advantage of those three properties I was talking about before: superposition, entanglement, and interference. And they can create an algorithm that's more efficient. Perhaps instead of n factorial, it's n squared, something like that. And in fact, one of the easiest ones, going back to that sort problem I was saying before, I was saying a sort was of that unordered list is n squared, I'm sorry, the search problem. The search is n number of things. There's an algorithm, it's called Grover's algorithm, that can do it in the square root of n. That's too complicated to go through here in the short presentation, but when n gets pretty large, you can hit this crossover point. And that's the key to quantum computer, is a quantum computer will allow you, not for some problems, and again, it depends on the problem. You won't use it for your email, you won't use it for calculating your bank balance, but it will allow you to develop an algorithm that's more efficient and take less runtime. So building a quantum computer is very, very complicated. There's many, many pieces. A lot of times we focus on the chip itself, as I said, whether it's a superconducting chip or a photonics chip, but there's many layers of software and control that are above that. So the quantum community is really large. There's lots of companies. I track over 200 startups that are working in the quantum industry. And of course, all the big companies are too. All the big computer companies are too. So there's many of them that are working on that. And just to give you some of the investments, the investment dollars are pretty large. Governments around the world see quantum as a very strategic technology. They all want to be the leader. And one of the things that amuses me a lot is I see a lot of these reports from various countries in Europe and Australia, whatever. They all understand that the United States took the lead with classical computing. We were some of the very largest semiconductor companies, the computer companies, the social media companies. But a lot of these countries don't want to see that anymore. They don't want the US and particularly California to dominate this industry. So they are all investing large amounts of money in the billions of dollars. So someone took an estimate in just in 2021 alone, it was $24 billion. The US itself is funding it roughly at a clip of about $1 billion a year through grants through our national labs, like Lawrence Livermore National Labs, Fermi National Labs, Brookhaven National Labs, all sorts of various national labs. But there's a global race here. And companies are all racing to see if they could become the leader in quantum. And of course, not only the governments, but the venture capitalists too. A new industry, eventually people are thinking that the industry will be worth tens of billions of dollars, and then create value that's in the hundreds of billions of dollars. I was talking earlier about some of the applications, but like drug discovery would be one of them. If you could use quantum computing to develop a new blockbuster drug, that alone could be billions of dollars worth of profit. So a lot of money is coming into this industry, and people are furiously developing new technologies, which of course, one of the things we report on in the website, the Quantum Computing Report. So people ask, what are the areas that people want to use this technology? Probably one of the biggest, I think long-term, one of the biggest impacts will be an area I call computational chemistry. The problem we have is that we can simulate like an optics design with lenses and whatever. We could simulate on a classical computer how it's going to bend the light and how the optics is going to perform. If I design a microprocessor chip, a classical microprocessor chip like Intel does, you can have a classical simulator that will simulate that. So if you have any bugs or errors, you can do that. If you're designing an airplane, you can come up with a computer that simulates the airflow over the wing. In chemistry, you can't quite do that. And the reason is because even though the scientists understand the formulas, they understand the mathematics of how it is, the number of different calculations you have to make are in the zillions. And even with the largest supercomputer, you can't calculate exactly how something like penicillin interacts with a virus. But people believe that a quantum computer can do that. And once you're able to simulate chemistry, all of a sudden that opens up lots of big opportunities for things like drug discovery, material design. One of the examples is the car companies, all these car companies developing electric vehicles. They want to simulate the battery chemistry. And the funny thing is today, we got all these electric cars, but scientists don't really understand exactly how the batteries work. I mean, they understand at a general level, but they can't simulate at the molecular level how the batteries work. And you need to do that to come up with new chemistry. You want to go from nickel cadmium to lithium, or to zinc air batteries. So what companies like Daimler-Benz and Ford and General Motors are doing is they're setting up partnerships with these quantum companies, and they're trying to simulate the different battery chemistries for a better electric car. And materials, of course, is used everywhere, so lots of people are working on various things. Machine learning is another big area where you want to use quantum to accelerate machine learning and artificial intelligence. The finance industry, they're always interested in using the latest technology that the people on Wall Street. They use it for things like portfolio analysis and risk analysis and those types of things. So there's lots of potential applications, as you can see on this list, for quantum computer. But again, I would emphasize that not every application, you still, quantum computers will never replace classical computers. You'll still always want to use classical computers probably for most of the world's calculations, but for very specific things like the ones on this list, you'll use them. Or you may use a classical computer and a quantum computer together. That's another hot area that people are researching. It's called hybrid classical quantum computation. So for people here in the optics industry, there's a lot of business here selling to these quantum companies, various optics, lasers. There is an organization that I belong to. It's called the Quantum Economic Development Consortium, QEDC. And it was initially funded by the government. Now it's sort of a semi-private thing. It's run by SRI, but we have task groups, and there's a components task group that's done reports on lasers, where lasers can be used and how they can be used for quantum technology. But things like fiber optics, single photon detectors. One company I'd point out, because it's a local company, is a company in San Diego called Cubatech. They make entangled photon sources and photon counters, those types of things. But again, it's a worldwide industry that people around the world are developing things. But many opportunities if you're a photonics component supplier. Here's some of the big companies that are investing in this. These are all big names. Again, here in Southern California, Amazon has a large facility in Pasadena. They are developing a quantum computer based on superconducting technology. Intel is working in Oregon. So many of the big companies, big computer companies, have their foot in this. Lots of startups. I was mentioning earlier, we track over 200 startups. This is an example of the startup companies developing chips and the technologies that they are using. And again, you can see the different technologies that people are using. And no one knows which one of these is going to win yet. It's still too early, sort of like a horse race at the 1 quarter mark. But it's interesting, and I have a lot of fun tracking it. Above the chip level, in terms of the system configuration, you have control electronics and control. How do you control the lasers, or in some cases, the microwave systems that shine down? The lasers will shine down on these qubits, on the atoms or the ions or whatever, and flip their states and manipulate them. How do you do the pulses? What are the frequencies of those pulses? What are the phases of those pulses? So there's companies that create this control electronics, and here's a listing of some of those companies. And then software, there's as many, well, maybe not quite as many, but there's a large number of companies that are trying to take the quantum hardware that I was just talking about and writing those programs to create those algorithms, again, that are more efficient than the classical algorithms. And these are some of the companies, again, that we work with, that we report on, that are trying to do that. And it's complicated because unlike, in classical computing, people are used to taking an existing system. Let's say I have an Intel microprocessor that runs at 3 gigahertz, and I upgrade my system to an AMD processor that runs at 4 gigahertz. The software is essentially the same. Very little changes in the software to get it to run faster and faster and faster. You just follow the path of hardware. The problem with quantum is you can't do that. You can't just take a classical system doing something, just make it a quantum thing and run that same software. The algorithms have to be completely different. So there are companies that are doing this, and these are the companies that will develop this software and then work with these end users, again, like Daimler or Ford or Merck or Goldman Sachs, those are all the end customers to help them. And they work with the experts, the people who understand the problem, to figure out a way to make the quantum algorithms work and accelerate their problem. So let me finish up and just talk a little bit about expectations. Quantum is still a very, very early stage. And in fact, the quantum computers are really not powerful enough to provide a distinct advantage over classical computers. For things that are in production today, if you really have to have a problem and you need to solve it quick, classical computers still beat quantum computers for what I call real world problems. So you may see some hype, and I see some stuff that just makes me cringe, like quantum computers will solve the climate change problem, or quantum computers will change everything. We're still at a very, very early stage. There will definitely be significant impact on society, but that impact is more like 10 or 20 years from now. But what's important is to get, reason these companies, like again, these end user companies like Goldman Sachs and Merck and Ford and the others are getting involved, is they know it takes a long while to figure out how to use these things, to learn how the technology works, to come up with your use cases, to come up with some what are called proof of concepts. All these things take years. So what they're doing is they are making these investments in terms of the education and the training. In many cases, they're hiring engineers and hiring scientists to research this stuff, because they understand that the hardware is improving by something similar to Moore's law. It's doubling in performance, or more than doubling every year. So the thing I want to leave you with is this thing called Amara's law, which someone came up with, and actually Bill Gates quotes this, which is that we tend to overestimate the impact of a new technology in the short run. Again, you see a lot of people in the popular press saying, next year, quantum computing is going to change the world, whatever. It's not going to happen. We're still in more of the training, education, proof of concept mode. But over the long term, people tend to underestimate the impact of the technology. And the thing I sort of say is, when the first computers were designed, again, in the 1940s and 1950s, some of the early pioneers of computer would never have predicted Facebook or LinkedIn or Twitter or social media or any of the things that we use today. They definitely would not have predicted, the cell phones, which are all packed with computers. So there's going to be a lot of applications for quantum computer in the long term. And again, I'm talking 10, 20, 30 years from now that we can't even anticipate. So we'll have a big impact in the world. So with that, I could talk for hours on this stuff, but Donn only gave me 20 minutes. But what I would encourage you is the website that I run is called this Quantum Computing Report on the right there. We have a newsletter that goes out every Sunday where we basically report on all the happenings over the previous week. The newsletter is free. So you can go to our webpage and you can sign up and you get on the distribution list. And every Sunday morning, you'll find out, all the new things. As I said, we have over 1,100 pages on the website. So there's lots of stuff to learn. And then if you really want to get in further, if you actually want to do a quantum project of some type or need some help, Again, this new company that I'm talking about, Global Quantum Intelligence, can help people. We can do consulting and provide reports and those types of things. So with that, I want to thank you for your time and hope you found this interesting.
Yeah. Oh, yes. What? Yeah. Let me get the microphone. So thank you so much, Doug. I'm going to try and get on to the next part of this presentation. Hopefully that'll work. That'll be the good volume there. And let me just get my presentation up. And it's really kind of a nice, I'll call it a segue maybe, because my presentation is going to follow his. Because as he was saying about the time frames, is many years, but we have to get our people knowledgeable about what this is. So we're going to talk about education and outreach. How do we get, I'll call it young people of any age, interested in this so that they can participate in this global quantum industry? So you all know who I am, so I won't belabor that. But I want to put a special thanks to Mark Bandauer here, because almost 30 years ago, I gave a presentation to this organization at IOLab. And it's been a real pleasure for me to be talking to you and be part of this kind of family, if you will. And so shout out to Mark. Thank you, sir. So for today, I just want to go through a few topics, get oriented about quantum education. What is the motivation for the process that I'm going to describe about doing education, creating the pipeline and path forwards for students. I'm going to talk about the Samueli Academy and their Schrodinger's Club, how I'm talking about quantum cryptography with help from the University of Waterloo, and then a couple of hands-on labs and qubit by qubit with IBM's QuizKit as how to teach people how to actually do quantum computing. So before I start into that, I just want to mention this interesting slide from Buckminster Fuller's Synergetics book from 1975. He was the guy that kind of invented or popularized the geodesic domes. Very interesting guy. And it's basically a curve. On the x-axis is time, and on the y-axis is human civilization progress. And so you can see here towards the middle is Isaac Newton in the 1600s, and the United States came into being, of course, in the 1700s. And then we have steamships and airplanes and rocket flights. So it goes exponentially. And these are actually on the far right side, atomic elements being discovered. So who learns about science and why? So not everybody learns about science, not everybody participates. Over the years that I've been involved in optics and photonics education, that's been the same case. So quantum is kind of an extension in some sense of fundamental optics. So how do we teach physics and to whom? So there's some books from Newton on physics and optics, the Feynman lecture series, and there was 3 books on quantum or modern physics that I studied when I was in college 40 years ago. So it seems to me that students self-select themselves to learn science, right? They decide they want to do it or they don't. So we can only teach it to those people who have selected it. And throughout recorded history, those people have to have time and ability to learn. They can't be, struggling just to survive and try and learn science. That's very hard. It takes focus. But many more people that have both time and ability to learn, that's kind of our subset of those people that we want to try and teach this to. But how do we get the message to young people that science is fun and interesting? Because they got so many things to take their attention that trying to do science for the vast majority of young people doesn't seem like something they want to do. So we have to find that subset of those students that are interested and able to learn these kinds of technologies. So back in 2003, I started the Optics Institute in order to try and find and do this outreach and start that. And so now I have this website called Optics Age or Quantum Optics Age. And if you go there, you can see I got the Welcome to the Ed Quantum Project. That's for community college work that we're doing. I have at the top there this whole section on quantum. So quantum for students, volunteers, education and work, cybersecurity, and some of my own explorations. And in a couple of weeks, Doug and I are going to be going to Washington, D.C. to the first Quantum World Congress, and we'll be talking about workforce development in our section, but there's many more sections talking about some of the other things that Doug talked about. So this is really going on worldwide, and I'm trying to figure out how to get it to the students. And also careers. So it's education and career pathways for the students. And so I created a little web page about career assistance. So these are some websites, including our friends at Optica, formerly OSSC, and these other web pages, websites you can go and look at for careers. And some of them are focused on quantum. Doug has jobs posted on quantum computing, reports.com. And there's many other websites. So I'm going to try and keep track of some of those for careers. But just a little brief history. 2005, there was Hands-On Optics, which was a National Science Foundation. Let's teach kids about optics. So that was good. You might remember our friend, Dr. Murdy. I created a kind of a character out of him to help get the word out to people like at the Discovery Science Center and others. But some of these tools are still available and still relevant from like SPIE. And this was, I think, from the Hands-On Optics program, and polarization, lasers, lenses. These things are currently available. They're on the website. And I'll show you in just a minute about why, like polarization, for example, is very helpful in learning about quantum computing and quantum phenomena in general. So on our website, the OSSC.org, we have this MPI. We were involved in the National Photonics Initiative, and that was back in 2012. So they started this many years before that, and then finally got it going as an initiative funded by the federal government. From that, they developed AIM Photonics, mostly from the Department of Defense, for manufacturing photonics chips, mostly in other types of photonic devices. And it says here that that there's still AIM Photonics is going strong. It's based up mostly out of Rochester, New York, but they also have a Western hub in Santa Barbara. And so they just extended, they've given them more money. It's actually been very successful. And now we have the CHIPS Act. So the federal government is funding that. And that some of those funds will also go to photonics and for quantum types of projects. But back to AIM Photonics, they have a education section on their website. And they have online courses, internships, summer academies, boot camps, virtual online things, all kinds of stuff. So they've been successful in the photonics area. And now we have the National Quantum Initiative. So you might remember, I'll show you in a moment, back in December of 2018, the federal government funded the National Quantum Initiative and set that up. And there's been subsequent refunding and subsequent federal encouragement for more people to get involved in the quantum workforce and quantum research. And you'll remember, hopefully a few years ago in June of 2012, where I met Doug, we had these two professors, one in theoretical quantum mechanics and Dr. Abi from USC in experimental quantum mechanics. So that was kind of the beginning of my journey. And so now we're going to tell you a little bit more about what's happened since then. This was from last month when I just gave a little slide about this, not knowing that I was going to come here and give a talk today. But I was at Optics and Photonics in August and gave a couple of one talk, and we had other things going on there. Been working with the Samueli Academy. They've started a Schrodinger's Quantum Club there. VitalLink has been a really good organization that we've done outreach for in the past before COVID, and now we're going to start that up again. And Mr. Bo Wang has been very instrumental in helping them, get through the COVID and relaunch their whole organization, their new website, and that's happening now. So we'll see some of that. Of course, we had the Nobel Prize in Physics, so that helps the whole quantum awareness come up because more and more people are talking about quantum because of the Nobel Prize. And we still have our program at UC Irvine. Brian Monticelli's still doing Pasadena City College. That program is doing much better now since COVID is gone. And I went down to DRS Daylight Solutions and heard some students from the UC San Diego SPIE student chapter talk about some of the things that they're doing. And I'm going to go down there on Friday, and they're going to actually have a quantum workshop on optical tweezers and how they're manipulating atomic particles and maybe molecules. So that's going to be very fun on Friday. And on next Tuesday, I'm going to be going to another high school in Newport Beach, Corona Del Mar, and talking to their programming class about optical quantum computing. So these things are going to keep coming up, and more outreach, and we'll get to more of that in a little bit. But for now, what I want to tell you about briefly, I gave this, presented a paper at SPIE on this quantum education and pathways, an open source modifiable presentation to high school and college students. So this paper that I presented to SPIE was about a presentation that is open source and anyone can use it to modify my presentation and then give it to whatever set of students you might be able to go out to in a high school or a community college or wherever it be. And so there's modifiable content. We talk about laser diffraction as a demonstration. There's a thing called Kahoot. Let's see. Kahoot for school. So the students are very familiar with this. It's kind of a way to get the students interacting with the presenter and thinking about the material. So you do a couple of these quizzes in the middle of your presentation, and then they use their cell phones to respond. So I learned about it through the Samueli Academy, and I've used it a couple of times, and it seems really good. And I understand actually the folks at Corona Del Mar High School, they do the same thing. So a lot of high school students are using this as a tool. You provide the content. So it's very kind of exciting for me. We also did this other paper and a presentation in SPIE and optical engineering and at the conference about quantum technician skills and competencies for the emerging quantum 2.0 industry. So again, how do we get students, mostly young people, but age is not any kind of a real barrier because veterans and people getting out of one career into another career, we can do this through the community colleges. So that's happening. It's starting in Central Florida, but there's a professor at Pasadena City College that's involved with the program as well. And what was the motivation? So part of the motivation for this paper and for the future work is to reach out to K through 12, because those are most of the people that are going to go to the community colleges or even universities. And we want to encourage them in the high school and maybe the middle school to learn about quantum, make them aware of what exists, make aware of the education pathways and the career pathways. And so we want to work with as many organizations, whether it's like SPI student chapters, Optical student chapters, IEEE, and local nonprofit organizations that are already working with schools and industry in order to make that connection in other industries. So we can use it like with VitalLink I mentioned. We can work with them to get the word out to the schools and the young people. So back in 2014, I published a paper and did a presentation about this optics photonics education pipeline. You might remember if you were around here, I did some presentations on the optobotics and I had a drone with video on it. Well, that was all the rage back then. Of course, now everybody's got drones. But now I use the same pipeline to include the quantum. And so we have the quantum workforce for Q12, Action for Community Growth, that's NSF funded. the National Q12 Education Partnership, of course, the Ed Quantum program, and Qubit by Qubit, which is a online quantum computer education program for high school students, which myself and my young friend Andromeda there, I'll introduce her in a moment, are actually taking now. So learning how to actually program a quantum computer now. Anybody can do it. It's open source. IBM funds it all. And there's other companies that have similar types of things, but IBM is the big blue giant in the industry. But there needs to be more than just online or computer programming, because quantum is so much more than that. So hands-on, like lasers and diffraction and atomic spectroscopy, those are the types of things that I really enjoy. And I say that the quantum industry is built on top of the optics and lasers, photonics, semiconductors, and other general physics fundamentals. So it's good to get young people understanding as much as we can about these science and technologies that underpin the entire industry. So the path forwards, I recently refound Optics for Kids, and that's sponsored by OSSC, Optica now, and they actually, let's see, hang on a second. We'll go back. So I'll come back to that in just a moment, but the Samueli Academy, they started a Schrodinger's Club, which is a quantum club where I've been mentoring them and going there several times already to have hands-on demonstrations as well as virtual type things. VitalLink I mentioned. I've come across, like I said, the Corona Del Mar High School. I'm looking for other high schools to go visit locally. On the university side, through SPIE and Optica, their student chapters, reaching out to them. So just like I mentioned, UC San Diego, we're going to be at UC Irvine next month, the Optical Society. So those students will be coming. They're reforming their SPIE student chapter. So there's more of those types of things to happen. And then again, this Quantum for Kids, Optica, they actually put my website, Quantum for Students, on their website, Optics for Kids. And I just found that yesterday or the day before. So I was very happy to see that Optica is on board with what I was trying to propose, and SPIE is doing something very similar with their student chapters. So this modifiable content and the other resources I have for students is getting out there in the optics and photonics world. And next May is education and technology and education and training in optics and photonics 2023 in Cocoa Beach, Florida. So hope to be there, and maybe there'll be a lot of educators there. And I'll be hopefully teaching them or talking to them about quantum for high school students. So I have my young friend Andromeda. Can you just stand up for a minute in case some of the other people haven't met you? She decided back in June of last year, I think it was, June of this year, when I did a presentation there about this, one of the call to actions on one of my last slides in that presentation was, if you'd like to do something about quantum and learn more about it, you can start a club or join a club, but they didn't have a club. So her and her friend decided they wanted to start a quantum club, and they did. And it's going well, and it's about to grow even bigger, because I think we're going to talk to the chess club, because there's actually quantum chess is available online. So we'll see where that goes. But these photographs here, the one on the top right was from an open house that happened a week ago. And so she had a couple of the posters there that I had donated to the school. And the other pictures, you can see some of the students actually working on the hands-on diffraction grading and spectroscopy experiments that they're doing in their lab.
I gotta ask, you don't put any cats in boxes, do you? Wouldn't that be obvious?
No cats in boxes. That was a thought experiment. I don't know if people have actually done it, but I've never done it. I kind of like cats. I don't. Anyway, one of the things that we teach the young people is about quantum cryptography, and we use polarization in a hands-on laser lab. So I won't go through too much of this. But quantum cryptography from University of Waterloo, I took a program with them last summer and started using some of their material, which is quite good. The role of probabilities, what is superposition, how come you can't make two incompatible measurements at the same time, like momentum and velocity, position and momentum, and quantum cryptography. What is that based on? Quantum measurements. So trying to teach the young people something that makes sense to them and they understand a little bit about cryptography and hacking. So those words, they're like, oh, what's that? Quantum. Oh, you can do that too. And so you kind of get their attention. And then we literally do the experiments with the polarizers, which is similar to the spin polarized electrons in the Stern-Gerlach experiment. And as Doug mentioned earlier about quantum key distribution and Alice and Bob in communicating and what happens with the eavesdropper. So we teach them that. We have them go through a little experiment using that, talking about measurement disturbances. So if you have a polarizer in the middle trying to make a measurement, it disturbs the polarization state. And then the no cloning theorem, we describe that to the students. There's a little matrix about basis. If you're vertical and horizontal, it's like a coordinate system. So you can measure it in coordinate system that's vertical and horizontal, or a coordinate system that's diagonals, or any other kind of coordinate system based on whatever the geometry of your system is. This is the hands-on polarization experiment, some photographs of that. So you can see the spot on the top left. No, it doesn't go through the polarizer. The next two goes through the left polarizer or the right one. If the light goes through both, then it's all blacked out on the bottom right. The same photo on the left. But if you put another polarizer at 90 degrees to the other two, 45 degrees, then light comes through it. So that polarizer in the red square is actually 45 degrees from the other two. So light goes through, so it's making that disturbing measurement. That's very disturbing. Right? And you can do the same thing with lasers. So I give them the laser pointer and they can do the same experiment. I used a deck of OSSC business cards with a rubber band to hold the optomechanical component that holds the polarizers. Very low cost, and it's good promotion. And then on the right, on the left-hand side, the vertical and horizontal polarizers block the laser light. But when you put the polarizer in the middle, sandwiched in between at 45 degrees, then the light comes through. So that's kind of interesting for the young people to see what's going on as we experiment and explain polarization and how that is part of quantum computing or quantum communications. Also talk about atomic spectra. That was a pre-quantum mystery. Why were there discrete energy levels in atomic spectrum? Talk a little bit about distribution patterns, diffraction gratings. I have 100 line pairs per millimeter and 50 line pairs per millimeter. So those two different diffraction gratings diffract the spectra or a laser beam at different angles. Show them about that. Get them to do some measurements with the laser and diffraction gratings. Oops. Have some very nice lamps with the diffraction gratings in them, specialty bulbs. So just kind of get them the stimulus, their visual stimulus, like what is going on, what is that? And these atomic spectra sources, you've probably seen these. These are some photographs I took through the diffraction grating of those spectral sources. And I'm not sure how well you can see those on the screen, but in real life, they look pretty cool. And again, it stimulates their imagination. It stimulates their thinking as to what's going on here and how is that part of the whole quantum world. This slide is the homepage for Qubit by Qubit, Training the Future Diverse Quantum Workforce. And if anybody here in this room is or online, if you're interested in anything that we've been talking about today, this whole Qubit by Qubit and the IBM quiz kit, that's all open source. The Qubit by Qubit is a program you can bring to your school. or educators can bring to their school. The IBM Quantum Summit they had in 2022. They're talking about what's new. And on the bottom left-hand side, you can see it says, get started with IBM Quantum today. And on the right-hand side on the bottom, it says launch QuizKit runtime on IBM Cloud. What that means is that anybody, anytime, you can go on their website and you can start learning about how to program a quantum computer. They have tutorials, videos, all kinds of great information that's available. This is a screenshot from my, when I log into IBM's quantum computing lab. And you can see in the middle there, I've done some homework and some lab work. I'm actually taking the qubit by qubit course. It's geared towards high school students, but because I want to go out and teach high school students this material, I should learn it first. So this is a homework assignment for a couple weeks ago, a lab work. So it's all done in Python programming language. So if you're not a programmer, Python is not that hard to learn, because if I can learn it, then it can't be that hard, because I'm not a big programmer, but I'm enjoying it. And so this is Doug mentioned something about gates. They have, a gate is where a qubit is going through something. It's going to do, this gate is going to do something to the qubit, like it might rotate it around an axis this, rotate it around an axis this way. This is the block sphere that Doug had mentioned within the qubit QuizKit program. And so it literally shows you, if you do an operation, what does that operation do to that qubit? And what is a qubit anyway? I'll answer that in just a moment. But this is like if you have a whole bunch of gates or circuits, it's a quantum circuit. What does a quantum circuit look like? Well, diagrammatically, it looks like what you see here on the bottom. And this is a histogram on the bottom right, which tells you the probability of the qubit being in a particular state after it's done an operation. So, in summary, kind of went through very quickly a bunch of things about education and outreach for the quantum industry. And like it says on the bottom right in red, would you like to help? And if you'd like to help, maybe there's a SPIE or Optical student chapter in an area near you at a university or college. So if there is, and you think that those students might be interested in quantum, then I can help get them involved, get them material, help them do outreach to high schools in their area. And if there's local nonprofits or schools in your area that you're interested in maybe bringing this information to them, and see if you can get, all you need is one teacher, maybe two is even better, that might be interested. And then once they think they might be interested, then I'd be happy to help get them involved, get the information, do a presentation or anything like that. And those materials and guidance, they're available now. And these are some of the things that I mentioned earlier. But with that, I do want to say thank you very much for your time, for your attention. And I think we can be open for questions, both from in the live room and online.
Targeted for high school students. How young do you think a person could be and still get something out of this?
So different presentations and materials for different age young people. So I actually have a presentation for middle school people, which is called Rainbows, Stars, and Atoms, and how they're related. Because rainbows, young people, at a younger age know what a rainbow is. They have an idea about stars. They've probably heard the word atoms. So we don't get into a lot of the other discussions about diffraction gradients and atomic spectra and getting them programming. They'd have to be old enough and knowledgeable enough to do programming in order to do quantum programming. That's typically high school. Oh.
I'm kind of curious, it's like eventually we're putting this pipeline going through the university. Do you have any thoughts on
how when these kind of subjects really get much more in-depth and complicated, and how do you prepare students to get ready for those, specifically the mathematical rigor? I would imagine a lot of linear algebra and multidimensional calculus are needed for a quantum mechanics class, at least for what I remember from that in my quantum optics class. Where does that how do you follow through that transition when you actually start taking these?
So there's two answers to your question. Let me rephrase the question so that people online can hear it. Bo's asking, there's a certain point in the educational process where more mathematical rigor is needed to really get in depth with quantum mechanics. And that's true. As I mentioned very early on in the presentation, students will self-select themselves for whatever it is they want to do. So if they want to go down the path of theoretical physics or high-level math, then that's available. That's available now. They will self-select themselves for that. But in the quantum world, in the quantum industries, there will be many more higher level applications where they won't need to have that quantum rigor. They'll just need to learn about what can quantum computing do in their particular application, and they'll need to find their way to be involved at the appropriate level for what they want to do. And I think there's some things online here. So let me see if I can figure out how to go back. Great question, answer. I don't know how to, where's my mouse?
By the way, linear algebra and multivariable calculus are now used. No, they're not. I teach college. I will assure you they're not actually there. What's there is something that has that word of the syllabus, the words typed on a page. I can assure you that those things are not in the books. Yeah, I sort of wanted to push back a little bit as long as we're talking about who needs what kind of math for what part of this pipeline. I mean, obviously you need linear algebra and differential equations, partial differential equations, and a whole bunch of other things to really get advanced quantum mechanics. But when you say, well, to figure out where it fits into your application, where quantum computing will fit in, I mean, at this decade or so of quantum technology, figuring out what an application will benefit from a quantum algorithm as opposed to a classical algorithm still fundamentally requires quite a bit of math to know enough about what kind of problem am I posing, what kind of calculation is being done here. Now, once we get to the stage where quantum computing is more of a utility, it's software that you download. You don't need to know a lot of math to know what type of software you need for many applications. A lot of the time you don't. So I think that if we're talking about things that are specifically quantum as quantum, I really don't think that there's any way around a lot of the math, at least for the next few decades. I think that the real value here in talking about quantum at the high school level is not, oh, we'll give them the simple version of the Schrodinger equation. It's the motivating factor of all of these things are out here, and there are many facets to this field and industry. Go learn more math and science. Not, oh, well, we'll teach you enough about spin right now to go and start writing elementary quantum code. It's a motivating factor.
So you're sort of right, but there's also some differences too. What jobs in quantum, and a lot of different jobs. Very high level would be one of quantum theorists, absolutely need very, very advanced math. But one of the things we're studying actually in the at the technician level, these are all machines. Screw the screws together to wire it up. To run, you even run very simple calculus.
saying that that is fundamentally preparation for quantum is like saying that someone who works in the metrology lab at a company making things for ophthalmology is really an expert on the eye or is being trained. I mean, at one level, of course, they're part of eye care. And that's lots of things are part of lots of pipelines. But to say, oh, we're really preparing them for eye careers when we train them how to work in metrology for ophthalmic products, you know, they're not really thinking about the rest.
From the standpoint of workforce, you know, where the job opportunities are there. But one of the things that's happening right now is all these end user companies. Many of them have what are called subject matter experts. People are experts in battery chemistry, but they don't understand quantum. And what are they doing? They're partnering with some of those software companies that I showed earlier. And that's where that expert piece comes from. But one of the things that people are working on now, again, at the software level, is ways of developing software that will abstract the problem so that you can enter it at a higher level problem, a higher level. And I'll give you a very concrete example. There's a company in Spain, it's called Multiverse Computing, that specializes in developing quantum applications for the financial. And one of the most common things that these banks want to do is called 10 different stocks. And I want the mixture of stocks that give me the highest return with the lowest possible risk. And there's but Multiverse has created a tool where input is at the spreadsheet level. You take an Excel spreadsheet and various criteria, and maybe the stocks and that type of thing, and it will automatically translate that into a quantum program. So again, the end user doesn't have to understand all the mathematics, all the stuff behind, you know, that does that. And that's a big area for software companies right now is to try to make quantum easier to use because, you know, quite frankly, it's a big roadblock right now. Part of the reason that might be is because people find it very, very difficult to translate the problem at the high level to these gate levels, you know, at software companies are working on that, and I think more progress in the coming years.
So you're talking about that travel and sales.
Yeah.
And it seems like there's like two classes of problem. One might be to most quick, oh, sorry. Yeah, you're talking about that traveling sales. It seems like there's a problem. It would be to best solution, and the other one would find a good route to acceptable solution. Does quantum computing lend itself to that second problem?
One of the issues with quantum computing, I didn't get into it, is there are a lot of errors. One of the reasons quantum computing is so hard is because there's a lot of errors that happen. Program, you can run a quantum program 100 times. Maybe you get the right answer 90% of the time. Maybe you get not the right answer 10% of the time. But people understand, you know, and that's what some of these experts do, is a lot of times, maybe the second or third best solution is still okay. And even though you'd like to get the best solution all the time, you'll never do that. Quantum computers today, actually, typically when people run programs, they'll run it 100 times or 1,000 times. See all the, you know, they'll plot out all the various answers they get. And then if the quantum computer is good, the answer that comes up most frequently is the best one. But you'll get a lot of, or maybe at least one of the best ones. But in the real life, many times coming up with something like that's the second best or third best is still very, very good solution.
So this is Alex. Talking about the market for quantum computers as computing devices, but in quantum information technology, the other big application that's been out there for probably 2 decades now is quantum encryption. Is that market now just at the industry level completely just so completely separate that you're not covering it, or is it very tightly integrated with the market for quantum computers as computing devices?
Yeah, actually, I do cover it, but I just couldn't talk too much about it. It's a 20-minute presentation. But to do quantum networking, the biggest issue we have though, called the long distance call. In a classical network, say from here in California to New York, you go over a fiber optic cable, the fiber optic cable has losses. So the communication companies do AT&T or whoever, will put repeaters. Every amplify it and reset it out in the next post. The problem we have in quantum is that no coding theorem I talked about before. You can't do that. So what people are doing is a couple of different solutions. You can send the signal up by satellite and have it come down. If the space loss is a lot less than the loss in fiber optics. There are things called trusted nodes. Under guard, so no one can interfere with it. It'll have one of those repeaters similar to classical. That's, for example, what the Chinese are doing. They have a line that goes from Shanghai to Beijing, but it's all using these trusted nodes, those types of things. Or there is a way of doing what's called a quantum repeater that takes advantage of quantum phenomena, but it's in a very, very early research stage. No one has built one successfully yet, but longer term, I think people will. But that's the thing right now that's limiting quantum communications, is the long distance problem.
I guess what is that since the processes are still at a fairly early stage and the actual competitiveness of classical computers is still questionable in some cases, to what extent are companies investing in quantum because they really have the sorts of their finance people can apply the sorts of discount rates to make a 20-year investment worth it, versus to what extent is it really is sort of a cross subsidy with their security. Like Goldman doesn't care, well, Goldman cares about a lot of things, but Goldman has secrets that are worth protecting, even if the only distance they travel is from Lower Manhattan to New Jersey. So there they have this sort of data where it's worth where the distance is short enough that they need a good quantum security group. So, and I'm not necessarily asking specifically about them, but in general, to what extent is it really an investment in something that might not be there for 20 years versus a cross subsidy with the security product that they're using today?
Okay, so yeah, let me talk about the security issue. That's very interesting. So today we use the internet and we use encryption technology called RSA. And RSA is a way of exchanging information without me having to travel to you and give you the key. Amazon, I want to charge something on Amazon. I don't have to give them an encryption key before they can accept my. So that was been put in place over the past 15 years or so on the internet. one mathematical problem, and then it's hard to factor a large number into semi-prime numbers. About 1995, a mathematician by the name of Peter Shor came up with an algorithm called Shor's algorithm. And he figured out photography that we have today. So people are really worried about that, particularly. So you say, well, you know, yeah, but I need a quantum computer that has 20 million qubits, and today the largest quantum computer has like 127. I'm worried about it. There's one small problem, and it's called harvest today, decrypt tomorrow. I could take, you know, someone could be tapping that line of Goldman Sachs and store all that encrypted information and put it on a hard drive. And even though I can't do it today, I can save that hard drive for the next 10 years. And 10 years from now, when those large quantum computers are available, then they can break it. And depending on the type of information, it does require information to have what's called long shelf. Things like health records, for example, social security numbers, yeah, all those stay around for decades. You know, plans for the F-35 fighter, that's still going to be valuable 10 or 20 years from now. And you know, people are worried about this problem called harvest today, and you know, the U.S. government is doing that right now. I'm sure all of our, you know, foreign countries are doing that now. So there is a move, even though it's not an immediate thing, to come up with what's called quantum resistant communication. President Biden, I think, has told all the federal agencies they need to start looking at it now. And the federal government, the entire federal government needs to have in place quantum resistant communications by, I think it's 2030 or 2035 or something like that.
Why I asked about quantum encryption, which is not going to be. I mean, I'm sure it has its own shortcomings, but the Shor algorithm is not an attack on quantum encryption. So I was asking is, are companies investing in quantum really to build up their quantum encryption, or is it really to have an algorithm in place in 20 years?
I think it's more of the latter. I mean, quite frankly, a lot of these quantum people at banks, they have two separate groups. They have a cybersecurity group inside of the thing, and then they have a like an app. And in some cases, there's two separate groups. So I think the people working in quantum computing, working on these algorithms, are really doing it so that we can have something valuable that is going to use it all. Not necessarily because of cybersecurity, but that second cybersecurity group, they're absolutely working on this. And by the way, primarily, the fundamental way we're doing that is not necessarily using what's called quantum key distribution that sends entangled photons over fiber optic cable. They're using new algorithms. There's a whole bunch of different classical algorithms that the National Institute of Standards and Technology has been looking at that will be able to encrypt similar to RSA, but so far that no one's been able to figure out a quantum algorithm that can break it. Yeah. They realizes if they put it in the back door, then some of our adversaries would find that back door eventually. So they've instructed all of their vendors, for example. They've instructed all their vendors to use some of, start looking at some of those missed algorithms.
Yeah, I want to thank Doug and Alex. That's a great conversation. I do want to mention that I wrote an article about this for kind of the general public. It's on my website called quantum computers and cybersecurity applications almost a year ago or something like that. And there's a lot of references that, go to all the papers, a lot of the topics that you were just discussing. So if you want to dive into that a little bit more. But I think at this time, John has something he'd like to say to the members. And Doug, I think if you could join us up here for a moment.
First of all, are there any other questions from anybody? Okay, then I want to ask a question. Okay, now, so this whole quantum world kind of seems otherworldly. We have a lot of companies which I was surprised to see. To me, I read a lot of papers, and I have never seen quantum in a paper. I'm wondering, where does this all come from? So where's the research done? Are you in what journal? Are you in physics journals or optical journals, or where do we find the research, and where did you find all these companies? This seems like we have, many of us here, we see a lot that's going on in the optical community and beyond, but this quantum is a little bit different. And I haven't seen it. In fact, I had a laser scientist who I worked with, and he developed an extraordinary new laser. He switched over to quantum. And I was like, why? I mean, and how? And he said he read courses on Coursera and MIT open course. So I'm thinking, is this really the way to go? So where is so if you are talking to a group of experienced professionals in the optical community, how do we find information that's at our level so that we can understand where this current application set is and where it's going?
Well, I guess my first recommendation would be go to the website, quantumcomputingreport.com website. I have a whole section, a whole page called education that talks about many of the programs that Donn has. You can look at those. We do track research. I have a section, a page, it's called Q-Nalysis, QNALYSIS, where we comment, we analyze various quantum developments. And one of the things that we publish at the end of every month is something called Research Roundup, which will show like a dozen papers that we found over the last month, both in hardware and software that talk about quantum. I will say that if any of you are familiar with Archive, ARXIV, there are a lot of quantum papers on Archive. And actually I have another link on my resources page to one guy who summarizes all the archive papers that they found. So it is out there. I assure you that, an archive and Nature Communications, sometimes in Scientific American, a lot of the journals are out there. And you can find many of those sources on my website.
Yeah. I would add to that, optical engineering, SPIE journals, Optica, even the magazines, the optics and photonics and the SPIE professional magazines. I see quantum articles all the time now in not just the scientific journals, but the magazines and, periodicals that come from our professional organization. So it's just, for me, it's
You might
really,
want to plug, there's a meeting Saturday in Halifax.
Yeah.
The people are interested, there's a meeting in Halifax Saturday for the club devoted to quantum industry applications.
so, John,
There's always.
Yeah.
Okay, so are there any more questions? Okay, so.
I seem to remember this, that we had a thing about the roadmap, and that we were going to take advantage of the roadmap we made. What's going on in this is in the roadmap that we made. Wasn't that part of the quantum initiative? That it was all laid out what we were going to do, education and that kind of stuff. I'm just wondering whether or not it's proceeding like we thought.
So I would kind of say yes in a way, kind of like the AIM photonics when that happened with the National Photonics Initiative. I was very skeptical because of my experience years before with the hands-on optics and outreach and stuff. And also the other manufacturing initiatives that happened in other technologies before AIM photonics, those seemed like they didn't really go anywhere. But the AIM photonics went quite well. And I think the National Quantum Initiative is also going well. And I feel that way because I'm very biased in favor of physicists and people in the science and technology at the level that we participate, the optics, photonics, computer industries. And I don't know, I'm just very biased in favor of it, I guess. Do you have any thoughts on the NQI and how it's proceeding?
Well, it's definitely proceeding, but it, like any program, maybe government program, it's very dynamic. People are always looking at how can we improve things. And it's both stuff inside the government as well as outside the government. The commercial companies and the venture capitalists, they're always trying to invent stuff that is new. But the government, again, is investing a lot of money, particularly in the national labs. You know, again, the Department of Energy has national labs like Brookhaven National Labs, Argonne National Labs, Fermi National Labs, Lawrence Livermore. All those have quantum programs, and they've set up quantum expert centers, and they've developed partnerships with private companies to research various things. So there's a lot of work, but in some cases, the government's doing even more than what they said in the National Quantum Initiative, which is again 3 years old now, and they're thinking about things all the time.
So we have some online questions.
Okay.
So maybe we could read the question, and if you've already answered them, say so. Otherwise, maybe provide some words, starting with this one here from Kim Bates.
Yeah, the quantum preserving repeater is an active area of development. One of the things I reported on, you know, one of the key components of that is called a quantum memory. Is you have a photon coming in from one spot, maybe you have a photon coming in from another spot, and you want to do what's called entanglement swapping. But you got to synchronize those things because because they got to be both there at the same time. And there's a company in Brooklyn, New York, just announced the first product. It's called Connect, QUNNECT, that's developed a quantum memory. And with that, they can develop this thing called a quantum repeater, which takes advantage of another phenomenon. It's called entanglement swapping. And there are other researchers like in the Netherlands, there's an organization called QTech that's working on that. So people are absolutely working on this, but it's still very, very new technology. You know, probably be several years before it becomes a reality. Yeah, well, you know, like any human-based system, theoretically, QKD is can't be broken, you know, from a theory standpoint, but there are always ways of spoofing the system. You know, you could have the greatest QKD in the system and you may get a phishing attack. And if one of your people sees a message saying, hey, comrade, I'm from Google, please tell me what your password is. You know, that's QKD is not going to help you. And so there's a lot of things, even though theoretically it's unbreakable, there's a lot of things from the implementation side and just the human interface side that you're always going to have to look at. Will a quantum computer be able to eventually solve what's called NP complete problems in computing? We're not sure yet. I think there are certain problems that the quantum computer can solve, but as I said, there are problems that neither a quantum computer can solve nor a classical computer can solve. So I don't think it would be able to solve all the problems. And that's one of the things about working in the industry, you have to figure out where it can be used appropriately and where it just won't work at all. There's a comment on Google Scholar, ResearchGate, Science Direct. I think that was in response to your things. All those resources will list various quantum papers. I guess you can go to those websites, list quantum, and it will give you listing of things. I think. Just one question about commercially relevant courses and classrooms and to take. Maybe to just follow up some of the discussion we had about education and courses. Quantum technology does require certain areas of mathematics that you really would be good to know about. One is trigonometry. The other is understanding complex numbers. The other is understanding linear algebra. So some of those, maybe are high school level, maybe undergraduate level. But those are definitely important and very, very helpful to have. One of the areas where I might differ from Donn is a photonics biased. I will tell you that although, it depends on the technology, some technologies absolutely, understanding things like, photons and polarization and frequency, wavelengths and all those types of things are critical. There are other areas of quantum where they don't use photonics. So you may or may not need to have a good photonics background, just depending on where you work. I guess that's about it for tonight, I think, in terms of the questions.
Okay, so any more questions before we go to the next step? Okay, now let's go to the next step.
Where do we see a picture of one of these damn things? What, like, I want to see I really would like to see like pictures of what a quantum computer looks like. Like, is it a box on my desk? Is it a giant room? Is it? I just still can't.
Okay, I have a few on my website. One of the sexiest pictures is a picture of something called a dilution refrigerator. So for these superconducting systems like IBM and Google have, they have to cool it down to like 15 millikelvin, which is really, really, really cold. As I said, 1,000 times or more colder than outer space. So there are companies that sell these things. One of these refrigerators, by the way, might cost $800,000 to cool that. And it's based on using different isotopes of helium and mixing them together to be able to cool the chip down to that level. And the reason you do that is to reduce errors, because any thermal motion of an electron or whatever will cause errors. So all you have to do is go to a website, go to the IBM Quantum website, for example, or any of these things. And I guess Donn has one on his cell phone, for example. You can see it. It looks like a golden chandelier, a dilution refrigerator that looks like a golden chandelier. It has multiple levels. First level is room temperature, then it cools down maybe to 70 degrees C, then 4 degrees C, and the lowest level is at this 15 millikelvin level. And they really, really look cool. Yeah, and
This thing is like,
you look outside the box. Yeah, the boxes, depending on how it's implemented, roughly it's about the size of a refrigerator, or maybe maybe 5 or 6 refrigerators. Like company in Vancouver, Washington, D-Wave. If I remember correctly, I think their box is 10 feet by 10 feet by 10 feet.
like how many, I guess, optical transistors are in this box? Is it
5? Is it 1 billion? Is it?
The D-Wave has no optics. That's a superconducting based system. But again, they're measured in terms of qubits. And the funny thing is that the chips, right now, the chips are very, very small, like a semiconductor chip. And the D-Wave system has like 5,000 qubits on it. But it's maybe, this big. But surrounding it is all this cooling stuff, and all the stuff to cool it down, and then the control electronics. The control electronics just is these big rack panels that have waveform generators and of various types.
You mentioned the different qubit technologies. Now you're talking about this cryogenic IBM, and then you also mentioned the ion trapping and different others. And I guess they are all competing against each other.
That's correct.
Now, what is your assessment? Which one would be most successful? Would the optics be
So that's the billion-dollar question. The venture capitalists, if I could answer that question, venture capitalists would put all their money on things. The problem is that the technologies all have advantages and disadvantages. Some have better qubit quality. Some are more scalable, build more and more qubits. Others have faster gate delays. And again, no one really knows which one's going to win yet, which is why, as you saw on the slide earlier, you got 9 different technologies and you got 150 companies working in all those different technologies. But the thing is, you go to a specific manufacturer, they'll say, we got the right ones. You go to IBM, they say, oh, no question, superconducting is going to be the best. And then you go to IonQ, for example, which does ion traps. It's, no. Ion traps is going to be, everyone thinks theirs is going to be the best.
Same with the photonics.
Yeah.
I just happen to agree with that. Thank you very much.
Thank you.
Okay, now this is it. So any more questions?
Don't do that.
We're closing questions.
We gotta go home.
We're closing questions. Okay, so we are, as mentioned, we are a group of optical professionals. And we value having professionals and expertise within our field coming and presenting for us. And to that end, we provide each of our speakers with a 1-year membership to the Optical Society of Southern California. So you are now one of us,
Okay.
and we welcome you aboard.
Well, thank you so much.
And of course, crown.
maybe not right in front of the screen because they kind of like,
Thank you very much. Thank you so much, Kevin. That was.
Okay, so we thank our speakers and with this, we are closing our meeting. So thank you for everyone who attended.